So at this point in the program, we are ready to start with our roughing toolpath. Now, you could go ahead and bring in a Vise if you wanted super accurate verifications and simulation of the exact machine environment. I don't think it's going to benefit us much here. The only possibility of a collision here will occur when we are machining around the outside of the part. So we want to machine past the bottom edge of our part, and let me bring the print over here for a second. Our part is 873 tall. Our stock is theoretically 1 inch thick. It might be plus or minus depending on the stock used. So we've got basically just over 1/8 of an inch to hold on to in the vise. Now we might be holding on to a little bit less, depends on how high your parallels are. But basically when we cut down around, if we go down say 0.9, we need to make sure that we're not going down 0.9 into our jaws. Now as far as putting the vise into the simulation here, it's not going to affect what happens out on the machine. So I don't think that point of the simulation is going to serve much benefit for us here. But obviously you need to make note of how deep you are cutting around the part, especially if you're not the one running this part. You need to know how much needs to sit above the vise in order to not machine into it. Something to make note of in your setup sheets. Okay, so before we get too much more off topic, let's get into this OptiRough toolpath and try and make some tool motion. So I'm hopping into OptiRough, and first page we're brought into is geometry selection. So let's go ahead and do that now. And new for 2022 is this right-click option called Add Remaining Entities. And as you would expect, anything that's not currently added to a group, you can add those remaining entities to a group that you've right-clicked on. Okay, and so since I have nothing currently selected, everything is selected and put into my machining group. Stock to leave, I'm just going to go with 15 thou here. Again, you need to adjust depending on your machine and what you feel you need to leave on a surface in order to be able to finish it and clean the surface up afterwards with finishing toolpaths. Okay, so let's move along here, and we next need to talk about toolpath control. Now this one, again, we're going to be using our stock model to give this operation the area that it needs to cut. So with that, I'm just going to hop down here for a second here and show how we do that. So rest materials turned on. One other operation, and the other operation is our stock model. So with the stock model, this toolpath control works a bit different. Basically what's going to happen here is when we're using stock, this page is going to define the range in which we want it to search for stock. However, if we are not using stock, if this was disabled, our toolpath control is going to set the boundary for the machining region. So basically what we're going to cut. Now to try and explain this a little bit better, I'm just going to run through a couple different scenarios and show some different settings, and we'll see the difference in the resulting toolpath. So what we're going to do here for boundary change, the boundary change is basically the shape that's going to define for, when we have our stock selected that we want to look for stock, or if stock was unselected, the range in which we wanted to cut. So we can just, we can select some geometry and define the shape, or we can checkbox this guy here, which will make a silhouette boundary of our selected machining entities. So all this stuff in here, it's basically going to make a boundary from that geometry, so no extra work here for us. We don't have to come back in here and select loops or faces or whatever. So we can just checkbox this, much simpler. Okay, so carrying on with stock, we don't get the options for strategy here. The stock will set the strategy on its own. Then we have options for inside, center, and outside. So when I'm using this toolpath, what I'm going to do is I'm going to be going outside, and this distance here, again, is just setting up the distance outside of this boundary that we want to look for our stock to machine. So I can set this to 1 inch, I could set this to 100 inches. In our scenario right now, it's not going to change the resulting toolpath. Obviously, this is going to make a lot more work for the toolpath because it's got a larger volume or a larger area to search for stock, so there's no need to get this excessive. But let's leave this to 1 inch. So we're outside 1 inch and we're using stock. I'm going to green check this and notice the toolpath that we get. So what I'm going to do here just for demonstrations, I'm going to make a duplicate of this, come back in here, and I'm going to turn my stock off. Everything else is exactly the same. I only turned my stock off. Okay, green check. Notice the difference in that toolpath. So that is a lot different than that. So toolpath 2, using stock. Toolpath 3, not using stock. So as mentioned, when we're talking about this shape definition here, when we're not using stock, this is what it's going to machine. When we are using stock, this is the boundary to search for this piece of stock and, an area to cut. Okay, so I'm going to get rid of that toolpath here. We don't need that. That's not what we want to do. And we'll come back into this guy and make some settings to make this toolpath do what it is we actually need it to do to rough this part out. So our toolpath control, everything's good in here now. We don't need to make any more changes. Tool settings, I am using this preloaded 1/2-inch bull end mill. Now I have chosen a bull end mill, and the reason for that is, a bull end mill has a corner radius. Let me just zoom way in. So the corner of the end mill, the corner of the tool it has a rad on it. So the theory here is, well, not theory, but the point of this is this shaped edge is much stronger than a sharp corner edge. Especially if you're roughing, you're wanting to push that tool hard, cut material, get it out of the way as quickly as possible. So you're putting a lot of stress into the tool, and if you have an exactly sharp corner tool, that point becomes a weak spot on the tool, and that's where the tool is going to fail. It will break, and it will break into some obscure shape on this corner, and it will not cut optimally. It's going to create excess of heat. Excess of heat makes tools fail quicker. Things snowball, and basically, yeah, your tool is going to end up failing because the sharp corner broke and things just got bad. Now, speeds and feeds for this tool, I do have values saved in this tool already, so I'm going to come down here and click on reinitialize, and it's bringing in my saved FPT, or feed per tooth, and my SFM, surface footage per minute, and that's coming directly from the tool. So again, let me come back in here for a second, and I'll show you where I input those values, right in here and here, as well as the number of flutes. So I used a program to generate these values. We're going to come back and talk about that program a little bit more in a future video, because again, we are cutting a piece of 316 stainless steel. I'm assuming this end mill is a coated carbide end mill, so it's a higher performance end mill, not just your plain carbide. And these numbers, again, are coming from an application. More about that a little bit later, but that's where my speeds and feeds are coming from. Continuing on down, I've already got a holder defined here. It's just a 1/2-inch holder. The end mill's out 1.5 inches, and down to cut parameters next. So typically when generating your toolpath like this, you're going to put in just basically your best information that you have about the toolpath you want to create. You'll then obviously make that toolpath, examine it on screen, look at the tool motion, make sure it's doing what you want, and typically you're going to end up coming back into this toolpath and making any adjustments to make your toolpath better, make it do more so what you are expecting. It's not every single time that you go and make a toolpath and it's exactly what you want out of the gate. Okay, but there's a few things I do know that, yes, I do only want to stick with a climb milling motion. These optimized step ups and step downs, I'm not going to touch. I'm going to leave them at the defaults for now. My step over, again, I used this application to let me know that I want to do a 20% step over. This angle here is directly tied to these values here, so you can adjust either the physical XY distance step over. This is a percentage of the tool's diameter, and this is an angle engagement of the tool. So just 3 different ways to define the same thing. Pick which one it is that you want to define, and the other 2 fields will automatically update those values. Step down. So as the description shows here, how far do you want to step down before you start making your cut into the part? Now, this is going to relate to how far down the part do we want to cut. So we know we've got a 1-inch thick piece of material, and we're holding on to slightly less than 1/8 of an inch. So I'm going to assume that we can step down 900 thou. Okay, so we have no reason to step down any more than that. Okay, so 0.9 is our step down. Step up. We need to step up because, this is kind of similar to the shape of our part over here. And if we step down all the way down to the very bottom of our part, which would be over here, our 0.9 would be right here, and start cutting in, as soon as it gets to this wall, that's going to be the end of the toolpath. So we want to step up and cut in, step up, cut in, step up, cut in, etc. So here is where we set that value. So these red lines represent the step up. I'm going to go with 50 thou. It might be a little bit coarse, but again, we'll have a look at the resulting toolpath and make any adjustments if we think we need to. Next one down, mill vertical walls. So basically what this is going to happen here, if we were to check box this, when we do a step up, so this angled portion here, as we step up, we're going to cut in, step up, cut in. On a vertical wall, not always do we want to, we've already cut along this wall. Do you want to step up and cut along this wall again? Step up, cut along the wall again. So I'm going to be turning mine off because once the end mill goes around this whole part, We have enough flute to cut this entire wall on that first pass. So we don't need to be remachining this wall in the step up. So in our step ups, we're going to be excluding milling of the vertical walls. Next one down, minimum toolpath radius. So how small of a arc do you want to allow this tool to make? Now, given our geometry here, this middle section is pretty wide open. So we can get away with pretty huge arcs to get through that part. Now, this tool that we're using is 1/2 of an inch. And thinking back to our blueprint, these slots here, they were roughly 0.35 wide. So no matter how small we make this minimum toolpath radius, our 1/2 inch end mill is not fitting through these slots. So we don't need to try and make small arcs here to allow this tool to get into here, because the tool's not going to fit anyway. So we don't need to worry about getting super small. Now, the effect that this will have on your toolpath. So I did make a video about things to avoid in dynamic mill motion, and this is one of the things you need to be cautious of, and that's putting in an extremely small value into this field, especially if you are feeding at extremely high feed rates. This feed rate will be constant throughout the toolpath, and basically what can happen if you start making these really small arcs is your toolpath. Again, I would suggest going and watching this video. The toolpath is making small circles, but the feed rate is still generated on the original feed rate. And that small circle, the outside of the cutter, is in fact moving faster than the middle of the cutter, and some problems can occur. So just be cautious when you're making extremely small values in here. When you have higher feed rates on your tools, it can cause problems and tool breakage. Other things in here, micro lifts. So micro lifts, when we're getting from the end of one cut and moving back to the start of the next, if we don't retract rapid and recut, if we're just doing a cut across, reposition, cut across, reposition, that reposition, it's not cutting anything. We can feed a lot quicker. So I'm going to go with 400 inches per minute. And a 10 thou micro lift distance. So micro lift, just like the picture shows, after it's on the cut, it's going to lift off of that face by this distance. We're at this feed rate on the repositioning move, and it ramps back down in, transitions back to your feed rate, enters into the next cut. Okay, so I think we're good here for now. We're not going to dive into this keep downs or motion sizes just yet. We'll have a look at the resulting toolpath and come back and analyze if needed. Next one down, those steep shallows. So here's where we can limit the height and depth of our toolpath. Now, as mentioned, we don't want to cut all the way past the bottom of this part. We've got a vise jaw there that we don't want to cut into. So I'm going to limit the maximum depth. And I know the physical distance is minus 0.9. If you didn't know, if you wanted to cut to a certain edge, you can come in here and say Z coordinate of a point and say maybe I only wanted to go that deep right there, and it will return the value for you. But since we know the distance, minus 0.9, I'm just going to key it in. Linking parameters, all I'm going to do here is turn this down to, I'm going to go minimum vertical retract and just kind of leave it at that. Arc filtering is not a bad idea to turn on, and I'm moving my slider at about 60-40. And tolerance, let's talk about that for a quick second. We're leaving 15 thou stock on this model, walls and floors. Does this toolpath need to be that accurate? Probably not. We can get away with giving this a little bit more tolerance. That extra tolerance will make our toolpath smoother. We'll have less abrupt direction changes because of our arc filtering. So let's maybe go with a 5 thou total tolerance. And again, still a 60-40 split. I'm allowing arcs in all three planes, and I'll even allow some 3D output if needed. So if your machine does not support helixes in the 3D, you would want to leave this unchecked. Other than that, obviously, yeah, we're cutting stainless steel. We're going to want our coolant turned on here. I have not set this up for dry machining of stainless steel. I don't know, unless you do a lot of stainless steel, if you're doing one-off part, probably not something you want to experiment with on your one piece of stock. So yeah, cut it the right way, cut it with some coolant. And yeah, don't worry about breaking cutters or work hardening your material. So green check, toolpath's going to generate. And here's our toolpath. So at first glance, I think it looks fine. The part's getting roughed out. Let's launch into a back plot, and we'll start dragging through this toolpath. So this right there, I don't think I'm a fan of that. Why am I not a fan of that? Okay, so remember what we told this toolpath. We said we wanted to do a step down of 900 thou and then start stepping up. So this thing right away, let me expand this out, is cutting at a value of positive 47.5. Oh, sorry, 16.7. I was looking at the retract values there. So we're at positive 0.167, and it's cutting all the way across the part. So not great. So what's going on there? So that's problem number one that we need to deal with. Let's look out for some more toolpath motion here and see if we see anything else that's not great. Let me just back up here for a second. Notice this path right there. So in my toolpath display here, any cutting motion is going to be blue. Retracts are yellow. Feed-ins are green. Lead-outs are red. And I believe transition values will be a brownish color. Okay, so notice this. We've cut all the way along this wall here, and it's all blue. And as we start to step up these walls, notice the motion right here. So that motion right there, it's not blue. That's not a cutting motion. That motion right there is going to be the repositioning or retract motion. Sorry, not retract motion, but microlift motion, where we're getting that 400 inch per minute feed rate. So we're off of the material. We're moving from here to here at 400 inches per minute, as opposed to way back when we're cutting right there. That feed rate is going to be our 25 inches per minute. So you can see where turning that checkbox for mill vertical walls off is saving us having to recut over this wall at 25 inches per minute. Let me fast forward here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 times. So all this motion here is at 400 inches per minute instead of 25. Obviously, that's going to save a lot of cycle time. So back into this, analyzing the toolpath. Notice we've got this cut going around the bottom of the part. I did notice at the very end, right here, it's doing that same toolpath again, but just a fraction lower for some reason. So that's not great either. So that's wasted tool motion. And the very, very top, that's all wasted tool motion. So we got two things to fix up. And I think everything else looks good. Like coming through the part there, nice wide sweeps through. Maybe when we get this cleaned up here, we'll be able to get a better idea of what the rest of the toolpath looks like. So step one, let's fix up this top machining, excessive machining. What's driving that is the fact we're using a stock model, and the fact that our stock model, let me go to the front view, has stock above the top of the part. So what's happening in this dynamic mill is it's machining that top bit of material away to leave a consistent amount of material on top of the part. So yeah, sure, it would make more sense for it to get that on the way up, on the step ups, not a first very, very small step down. But given the combination of this stock, this part, the cut parameters, this is the way it's going to work, and we need to make some adjustments to it outside of the toolpath to make it do what we want. So what we have to do here to get rid of that excess motion on top of the part is lie about our stock model. So this stock model, I'm going to go ahead and come in here, and I'm going to take away the extra 20 thou material above the part. So I'm going to make this 0. Green check. Stock model goes dirty. It's rebuilt on its own. So there you can see the stock model is now exactly on the very top of our part. This needs to be rebuilt. We'll have to do it manually. So I'll click rebuild. And notice that first bit of motion is now gone. Okay, so that fixes it up. So that's another reason why there's times when you want to use two different stocks. So here I had to make an adjustment to the stock model to get the toolpath to do what I want. But when I go into simulation, I want my correct stock model being used in my simulation so I can see the very top of the part getting cut. I can see all the material getting engaged no matter what. So yeah, you can get away with using just the stock model, but if you're having to adjust that stock model to get the toolpath to do what you want, maybe your simulation now is going to suffer. Okay, so we solved problem number one. Let's solve problem number 2, which is this step right here. So let's go back over here for a minute. And what's happening here is we're telling it on our step down maximum 0.9. We're also limiting the toolpath here to minus 0.9. So the fix I've found for this here is going to limit the step down as long as our step down is bigger than that limit. So if we're only wanting to do that one step down, what I would do here, just for a round number, I'm going to say 1 inch. Cut down at the most 1 inch, then go about the toolpath. This is going to not stop that 1 inch step down at minus 0.9. The toolpath will carry on. I find this is only a problem when both values match. So that should fix that up. Let's green check, rebuild, and now we've got just the one toolpath at the very bottom of the part. So we step down, cut around, and everything else now is a step up. So beyond that, we've got some retracting and some repositioning, which I think we won't find much optimization in. So we've got some rapids over here, but these are not rapid transitions. These are rapids for next cuts. You can see on this side of the part, these brown lines, these are the rapid transitions. So we won't be able to get rid of these. We could change them into feeding motion, but we're not going to be able to get rid of those retracts. Let's have a look here at our cycle time. We're at 7 minutes in cycle time. That's not too bad. You can, if you're looking to shave every second possible out of your toolpath, obviously speeds and feeds and step overs are your main contributing factors. But if you've got your tool pushed to the limit on speeds and feeds, step overs, step downs, you can start dabbling with these optimized values over here. So maybe instead of by depth, we go to next closest. So we were, I forget what our cycle time was before. So now we're 7:58. So that's worse. I know we were less than that in the other method, so we can try by pocket. So we were 7:58. We're now 7:17, which I think was the same as before. We can try step downs by air. Again, rebuild, have a look at the difference here. 7:24. So you can see just by changing our repositioning methods and order of cutting, we're getting a vastly different cycle time. Now, different parts will benefit from different selections. And I'm going to stick with the theory here that if you're making one part, so you're doing a one-off, a difference of 15 seconds, 30 seconds in a cycle time of a toolpath is not going to make or break you in a one-off part. A one-off part, 95% of your time to make the part is going to come from setup, programming, inspection, and stuff like that. Your runtime is going to be the smallest thing. Even if you save 2 minutes in cycle time, you know what I mean? It's going to take you 3 hours to make this part. Is a 2-minute cycle time really that big of a deal? Probably not. So don't risk breaking your tools. So we're happy with the looks of the tool motion on this so far. Let's launch into a verify. Now in verify, I want to make sure I have a stop condition on for collisions. Anytime that this tool is detected of colliding with our stock, I want it to pause so I know something bad has happened. I'll turn this on over here. Let's do, well, color loop's not going to affect anything because we only have one toolpath. And we'll launch and play through. And everything looks fine there. There was no collisions. So you can see where we've cut. So there's obviously the little piece of material we're going to be holding onto in our vise. There you can see our step ups. And even though we are using a bull end mill, so we have a radius in the steps that we're cutting, we're still getting stairs along our part. So do you want to leave less? Then maybe you need to turn down your step ups. Keep in mind, if you do a smaller step up, that's going to generate more cuts. It's going to increase your cycle time. So it's either you live with what's there. We're still probably going to do a semi-finishing toolpath on these surfaces with a 3D toolpath. We'll do a semi-finish finish. Or you could refine these step-ups to negate the fact that you need a semi-finish operation for the surface toolpath. I'm going to stick with this. This tool is just going to rough this thing out, get the material out of the way, and we'll get into our finishing toolpaths after that. So let me just slide the print over here for 1 second, and let's have a peek at what we've got going on. So we've got this part. We're going to end up having all this material roughed out. We've left 15 thou on walls and floors. We talked about part distortion a little bit earlier, and then if that's something you need to worry about. And I think what we'll do here, we're getting pretty long as far as this video goes. We'll cover that in the next video. So next video is going to be, we're almost going to be repeating exactly what we've done so far. So we made a stock model that's used for stock to give to our OptiRough, which turns it into an OptiRest toolpath. So we're only cutting where there is material. And now that we've cut a bunch of the material away on this part, we want to do the same thing. Make a stock model that contains information about where stock exists or where there's stock left to be machined, which we'll do. We'll create a new stock model, and then we'll create a new OptiRough toolpath, which will be turned into an OptiRest based on the fact we're giving it stock material. And we'll be using a smaller end mill, one which will fit into these slots, and we'll finish rough out those. And that will then wrap up our roughing process for this part. So that and more in the next video.